Okay, so I'm going to look at some multiple threads here. So let's have a look at thread array. And this is almost exactly the same as our last example, except this time we're doing everything per frame. So we're going to create an array of threads. At the moment it's just one. And then we've got this thing here, which somehow I've managed to delete, called join. So we start the threads, and then join means we wait for the threads to finish, basically. It's a strange syntax, but there you go. And then we can just set the name here, because we know that all the threads are finished. So whichever thread finished last and change the name, that's the one we're going to use. So let's just see if this works. Let's make sure a thread array per frame is on. Okay, let's run this. It's just starting up. Okay, it's finished. Game object changed. Okay, that's all good. So let's finish that. Close it off if I can. That's because I'm doing it per frame. This is dangerous. Can I actually stop Unity now? Let's see if I can force this to stop. There we go. Always a good little tip there if you ever get stuck in type loops, just change the code and introduce an error. Right, so that was that working. And again, this is going to be another dangerous piece of code, because what's happening here is because we're in such a tight loop, it's not giving, it's stopping on the updates. So that means that the update frame is stopping in Unity. So that means we don't have enough opportunity to get in there and do things like stop and pause. This is why, again, another reason why this is dangerous. But anyway, let's try this out. So we're going to go in there and we're going to put 100 threads in here. Oof, here we go. This is going to cause me a problem stopping this. But anyway, let's just do it for the science of it. So what's going to come in here, and we're going to create 100 threads, and they're all going to be doing the same calculation. So this might be the last time we see this Unity before I have to kill it. So let's just save this, make sure I'm in the right place. And now let's bring our process back. I'm just going to go away as soon as I press run. So I'm not seeing an awful lot of activity, and it's all finished, but it's all been pretty even. So there's not a lot of work going on, can't really see it. There were 100 threads spun up then. Let's see if I can count the thread title. So it's just doing it per frame. And we can see that these numbers are going up. Our FPS is awful, which is because it's waiting on all these threads to finish every time. But we were doing a lot of work, so you can see these numbers going up. It's just that our FPS is just really poor. So it's really not a good idea to try and do these things on a per thread basis. So if you want a lot of compute power, we want to bring in a lot of compute power, but we want to do it on a per frame basis, are there any alternatives? So let's have a look what's out there, if I can stop this. Introduce an error. Good. Always a sneaky way of doing things. So let's get back to turning that off before I run it again by accident. And let's switch back to presentation. So our next thing we can look at is something called threading tasks. And one of the main things from threading tasks is it uses this concept of a thread pool. So previously I was just asking for threads and I had no real concept of how many threads there were on the system. I had no real idea of if my system had more or less threads than I should be asking for. I would just ask for a load of threads and just hoped everything would work. That's obviously not a great idea, especially given the numerous type of devices that Unity can run on. You really don't want to be doing that. The other thing which we touched upon was just the overhead of managing threads. And creating a thread and destroying a thread is actually relatively expensive from a CPU point of view. And what a thread pool allows you to do is it allows you to create a pooling mechanism where you just ask for threads and it gives you to them if they're available, and then it can expand or contract even, although .NET doesn't tend to do that, at least not on Windows. But it will give you, make sure the pools are of a decent size and manage the threads, and you can also have different scheduling for different threads, and you start getting really clever with that kind of stuff. The main thing is you don't have to worry too much about it. You just kind of ask for it and it gives it to you. And if there's a delay, then there's a delay. But normally you get on pretty well with the thread pool. But one of the things is it still acts a bit like a normal thread. We're still not on the main thread. So we still have those sorts of difficulties. So what am I talking about here? Let's have a little look at a task. So we've had our threading array. Let's have a look at our pooled tasks. So what we've got here, again, very similar to the array thing. We've got 1,000 tasks that we're going to spin up. We're going to ask for to get working all at once. So they'll be coming from the pool. I'm also got a little cube object here. So if we switch back to Unity, we've got this little cube. There he is. Okay. And I'm going to use that because I'm going to start painting that cube inside the update. So I want to see that the update, the FPSs are actually doing something useful. So the first thing I'm going to do is I'm going to ask the computer that it's running on how many worker threads it's got and how many completion port threads it's got. Completion ports are something you can get tied up with if you use things like sockets and stuff. You can get things like port exhaustion and all sorts of nasty things, but we don't have to worry about that currently. It's the worker threads that we're more interested in. So it's just interesting to see how many worker threads we've got. So we're going to go into an array and we're going to create a number of these tasks, and they're going to run this do something thing again. And we're passing in the game object this time. But then there's a little trick to this one. So we can also say, when you're finished, run this function here, finished all tasks. And that's just going to bring a task in and it's going to set the game object. It's going to try to. So we're going to run that. And what we're doing again, well, in the do something thread, we're doing our same old thing, which is doing loads of square root calculations. We're setting the change name as we did before, so nothing particularly exciting there. Yeah, so we're going to run that and let's see how that goes. Oh, the update event. So in the update, we're just going to say that every couple of seconds, I just want to change the material of the cube. Right, let's see how we get on. So where are we? So we are on our game object, finished doing that. We've set the threads, we want the task, all tasks. Let's run that. So we can see the cube is going from blue to red. We've got, you know, fluctuating FPSs. but we are doing work and we are changing stuff. And there we have our get game object can only be called from the main thread. So if we look at that, we'll see that even though this continue with has said, okay, go and call this method, go and call this function, you write the game object, it can't do it. So this is still, when it comes back from the thread, it still hasn't gone back, hasn't synchronized back with the main thread. So it still can't do this work. So you can't do this. Well, that does not work. So we still have to rely on this update mechanism here, our kind of pseudo dispatcher, in order to get back onto our main thread, do work on our main thread. So there we are, it's still a problem. But when we run, we can see that previously when we had our threads, our FPS was just awful. Whereas now with the tasks, the pull tasks, we can see that our FPS starting off slow. There we go, now we're running. We got our cube changing color quite nicely. We've got our FPS is quite high. Just checking to see. Yeah, there's no work going on here, is there? So that actually it was pretty poor to start with. I'm quite surprised by that. Okay, we can see a large number of tasks starting. And then finishing. So while we're doing a lot of compute power, we are just not really helpful from a Unity's position. It's just too much in here. Let's try knocking this down to just to start with 10 tasks. Well, actually, the one thing I haven't shown you is there's 24 worker threads. So let's try that. So they all finish quickly, too quickly, and then they're not in here, but that's okay. So let's try an experiment here. So we got if we put the continue with back in, so the continue with, and we change the game object, that's fine. To new name, we can just say, rather than do that, do next run equals true. If do next run get rid of that. I don't like that. No need. Oops. Spawn tasks. So now once we've finished, we'll do another run. Let's see how we get on. Oh, tell you what, I haven't reset the counter. Finished counter. So you can see here we're spawning a lot. And our FPS is suffering. But it's kind of working, but it's not great. So we still haven't really got a really nice solution here. I mean, we're definitely utilizing. Boy, are we utilizing. But we're still, from a Unity's point of view, this is still not great. I just wanted to revisit the task method because I don't really understand why that was blocking. So let's go back to the task pulled. And what we have is start, just as a reminder, we've got a start here. We spawn some tasks and we loop over them, spawning them. And then when they complete, they fire a continue with. Now, previously, I was doing this spawning every time in the update frame. And obviously, there was something in there about just the overhead of creating it was really slowing it down. So what I've done this time is when any one task finishes, it will spawn a new version of itself. It's kind of clone itself. So if thread number 9 finishes, then it creates a new thread number 9, a new task number 9. And then it keeps on going like that. So if we run that now, so I've got 10 tasks running and our frame rate is much higher. And we can still see we're getting a lot of work happening. But the stats are showing our FPS is much better. And if we look at our CPU usage, we can see that, yeah, all my CPUs are getting involved in this. And then if we stop this now, we should see their use come down quite quickly. You can see the graphs going away. So hopefully that will show that actually the task method does have some use within Unity. There's one interesting thing I thought I'd quickly show you as well to do with this, which shows you something about how this is all working. You notice there's a flag here that has stopped. So in the on destroy, I'm setting this. Now if I turn this off, in fact, if I just comment out the whole of this, and run this, so we're starting off again, our FPS is good, our CPUs are starting to ramp up with their work, that's all good. And then I quit the Unity session that's running, and look, see here, our threads don't care what Unity says is going on at all. So those tasks are still happily running. They're going to carry on running, doing their thing, regardless of the fact that Unity is completely finished. So that's quite interesting. So hence I've had to put in the abort, just put this has stop flag in here, and then just recompiling will actually stop this thing, bring this thing back in line. And now when I run, press stop. You can see that it's conforming to what we need to do. So again, it's another example of why we have a bit more responsibility when we start working outside of Unity. So I hope that makes it a little bit clearer about how tasks work and how you can actually get them to work quite nicely. Another option is to use something called Async Await. And this is based on the task mechanism we just saw, but it uses an internal state engine that allows you to have some concurrency, but your code is much easier to read. And it's especially good for calling out to third-party APIs. So a lot of those, especially if they have a .NET SDK, will have async await methods that allow you to write much simpler code. And we'll take a look at an example of that as well. So let's have a look at async await. So here we've got our code again. We've got tasks again, because async await is built on tasks. We've got 1,000 of those again. We're going to do something slightly different here. So we've got start, and Unity understands async await pattern. So I've changed the start method to be an async task. So that's a little bit of a difference from void. We're going to say that we started, do our usual stuff, create some tasks. And then this time, what we're going to do is we're going to say, when all of these things have completed, we're going to wait for that to happen. And then we're going to change the name of the game object. And then we're also going to say start completed. Okay, so started, completed. So what task are we doing this time? It's slightly different. All we're going to do this time is we're going to say, please wait for 2 seconds. So this is going to stop this task from running for 2 seconds, and after 2 seconds, it's going to carry on. This is a bit like wait for seconds in Unity land. And we're going to change the name, and that'll be it for that. So if you think about what's happening here, so each one of these things is going to wait for 2 seconds. Now, if this was an array of synchronous tasks, that means that we're going to wait for 1,000 times 2 seconds. But if they're running in parallel, then we should, if it's perfectly parallel, then we should wait for exactly 2 seconds. Because the tasks are scheduled, chances are it will be slightly longer than 2 seconds, but we'll see what happens. And in the meantime, because we're waiting in start, our experience tells us that we're not going to do any updates. But we'll see that because we're using this internal async await engine, whilst this function is stopped, it's not going to prevent the other functions from running. So that's quite an interesting change. So let's have a look, see how we get on. So let's run this. Okay, we got started, completed. So that took roughly 2 seconds, got into this. Let's bring our systems back up. Let's see if we can do that quickly. I mean, it just doesn't really show, it's not doing enough effort. The sleep itself, the task delay, is a very kind of non-destructive function, so we're not seeing an awful lot of work doing. But what we are seeing here is the way the async await works, in that it's managing to do what it's been told to do and not block the threads at any time. So if we start this again, and if we carefully watch the cubes whilst we're in this started and completed bit, but let's up the delay a bit so we can see that a bit clearer. So let's come in here and make the delay 10 seconds. Let's just run that. So we got started and our FPS is running here, it's fine. Our cube's moving fine. So the update's working and the start hasn't finished yet. And there's the start completed. So we can see that the start has now become a non-blocking. So whilst it's holding, waiting for that to finish, it hasn't blocked the rest of the code working. So we can still our editor, and still do all the other things on the main thread that we're used to. So that's the really important aspect of Async Await. It frees up the main thread, and you can carry on working and doing other things. And this is why it's important for talking to third-party apps. So I've switched over to a little quiz app that I have. If we just run this, it's just a very basic quiz kind of question. Where was this house built? And you have to, who built it? And you can, oh no, got the answers wrong. Child Light Brigade, Tennyson, yeah. Okay, so it's basically a little quiz game. And this is using the Async Await pattern. So let's have a look at that. So in here, when we initialize the quiz, it uses this task run method, which is task factory start new, which is a way of creating a new task, and it creates it async. You can see here we've got a lot of calls to another service that are all awaitable. So if you take a look at this one here, load decks, going to here, you can see that it's going to call this thing called lists and blobs. So a blob is a term for a kind of a blob of binary data it's going to get from the cloud. And then it's going to just sort of process these and then download some questions, download some images for some questions. And what you can see here is it's all very kind of procedural based. It's just do a list. When that finishes, get the first one, download a deck. When that finishes, and we just move line by line. Now, in other mechanisms that aren't Async Await, you have to have lots of callbacks and lots of complicated code. And there's none of that with Async Await. It's just really simple kind of code blocks. And that's really the power of Async Await, is that you don't have to have these kind of chains of, oh, this is completed and waiting, and this is completed and waiting. Lots of kind of weird event handlers, and all of that nonsense has gone away with Async Await. And that's why it's such a powerful mechanism. So apart from the artificial thing that we just saw, we can see that, if we just look at download images, for example, we're just calling this function again, just straightforward as if it was a normal procedural function. And what it actually is doing is it's going off, it's calling this list blobs, we'll just go into that, doing lots of sort of complicated cloud-based talk, but basically it's just going to go off to the cloud and ask for a list of stuff to get back. And if the cloud is slow or a bad network connection, then this code is just going to wait for it to finish and then move on. But crucially, it's not holding the rest of the Unity to ransom. So it's not holding, this isn't working on the main UI thread. So whilst it's waiting to get this images from the cloud or whatever, your main API is still all functioning. You can press all the buttons, everything still works. So that's really where the main power of Async Await lies, is writing code like this. It's just very simple to read. There's again no weird event handling, no on callbacks, none of that stuff. That's all gone. A lot easier to write, a lot easier to read.